as we are learning about limits, an explanation of continuity and discontinuity is also needed, because a function is only continuous if the graph has no breaks, where at any x value there is only one y value. However, there are also graphs like the one shown here that are discontinuous. There are three main kinds of discontinuities, all shown in this graph. Firstly, over here, there is removable discontinuity. Here there is infinite discontinuity, and here there is jump discontinuity. So the first discontinuity we're going to talk about is removable discontinuity, which occurs at x equals 2. So removable discontinuity occurs when the limit of f of x, which is this function, exists, but it doesn't equal f of c. So at x equals 2, y equals -1, and there is no, and negative 0.5 actually doesn't exist on the graph. But the limit of f of x as x is approaching 2 from both sides is negative 0.5. So when we have this type of discontinuity, we can redefine the function of f of x to become f of c at that point. So we would take this point at -1 and we would place it into the function to make the function continuous. This is possible because the definable point is not a function and we wouldn't be changing any other function in the graph. Another discontinuity that occurs that is similar to removable discontinuity and is often mixed up for removable discontinuity is jump discontinuity, which occurs here at x equals -3. So jump discontinuity occurs when the limit of f of x from the left side does not equal the limit of f of x from the right side. So here the limit of f of x from the left side is not definable, but the limit of f of x from the right side is 0.7, and we can't redefine the entire function of f of x to become continuous, but we do have the option if a question asked if how we could make the left bound continuous. We can switch the discontinuity, so we could make left bound be continuous, but if we make left bound be continuous, then that means the right bound cannot be continuous because the entire function is never going to be continuous. And if this is confusing, an example will be shown later on in the video. So the final and third kind of discontinuity is infinite discontinuity, which happens here at x equals -1. So infinite discontinuity happens when one or both sides of a function have limits going to positive or negative infinity. So if the asymptote, if the function went all the way downwards at the same asymptote but went to negative infinity, this would still be infinite as a discontinuity. And if, say, one side did stop at some point on -1, but the other side still went to infinity, that means it is still discontinuous with infinite discontinuity. And so now that we've reviewed the three types of discontinuities, we can move on to some practice questions. So the first question is asking to find the point at C1 on g of x, which is this function on the right, with this graph on the right, at which g of x has a jump discontinuity but is left continuous. How should g of C1 be redefined to make g right continuous at x equals C1? So on g of x at x equals 1 right here, the function is left continuous. As you can see, this function includes 2 at 1, but is discontinuous at 1 because it excludes this y value. So this satisfies the first description of the question, because this is a jump discontinuity and it is left continuous but not right continuous. But the second part of the question asks how should x equals 1 be redefined to make g right continuous at x equals 1. So as we talked about before, we can switch the continuities, so we can redefine it and assign g of 1 to equal 3 instead of 2. But then this means so that this makes it right continuous, but then it means that it is no longer left continuous because there would be a hole here and then it would be filled in here once we redefined it. So I just summarized what I said over here in writing, so you can just review it instead of having to go back and listen to me explain it again. So the second question is number 5. In figure 16, determine the one-sided limit at the points of discontinuity. Which discontinuity is removable and how should f be redefined to make it continuous at this point? So at x equals 0, there is infinite discontinuity because from left bound, the function goes all the way to positive infinity, even though there is it is definable from the right side, but it is not from the left side. And since both sides are not definable and they do not equal the same y value, which is the definition of a continuous function, is that at one x value, both left bound and right bound limits equal the same y value. Since this does not happen, this means that it is infinitely discontinuous. And then at x equals 2, there is a removable discontinuity because on the function there is no definable point at x equals 2 because f of 2 actually equals 2, but the function, as the limit approaches x equals 2, the limit of the function would be 6, and those two things are not equal. So there is removable discontinuity there. So that it answers the second part of the question. And how should f be redefined to make it continuous at this point? Well, we can redefine f of 2 to become 6. So we would just move this point up there to make it continuous on the whole function, except for, of course, this side, which is never going to be continuous because it is one side is going up to infinity. But this part of the function in quadrant 1 will be continuous.